Why are we here? Where did we come from? According to the Bongo people in Central Africa, before us, there was only darkness, water, and the great god Bumba. One day, Bumba had a stomach ache and vomited out the sun. The sun caused some of the water to evaporate, leaving behind the land. Still uncomfortable, Bumba vomited out the moon, the stars, and then came the animals: leopard, crocodile, turtle, and finally, humans. This creation myth, like many others, grapples with the fundamental questions we still ask today. Fortunately, we now have a tool to provide answers: science. With the advent of astronomy, humans began posing more fundamental questions. What is life, and where do galaxies come from? We know they are always there, existing like vast cosmic islands, comprised of stars, gases, dust, and dark matter bound together by gravity. No one knows their origin, no one answers the questions humanity seeks. Now, humans must shoulder the responsibility of adventure and explore the nature of life, the essence of the universe. That is why James Webb has appeared, immersed in space. James Webb not only observes light from the past but also serves as a time hunter, tracking the paintings of the universe's formation. It is not just about observation, it is a journey deep into the memories of the universe, particles of beginnings. But can we trust what James Webb sees? There are things hidden behind the beams of light emerging from the past, and the story it tells is not just about the past but also about our present and future. Join us on this adventure to explore the mysteries of the universe's history and to better understand the dark beauty that we have only glimpsed a very small part of. Music, eyes transcend space and time. Telescopes are considered one of the most iconic scientific instruments ever invented. Few other objects can be easily identified both in terms of their external appearance and their purpose. Telescopes, those miraculous optical tubes, have transformed how we understand the world and its place in the universe. Certainly, their development would not have been possible without ancient advances in lens technology and accompanying optical theories. But the detailed and fascinating history is too vast to recount entirely here. However, we can begin to ponder the story of the telescope, a tool born out of this history. Starting from the late 16th century and early 17th century, the early history of telescopes is closely tied to the career of Galileo. In a time when these special spy glasses were being used as tools for observing battlefields, Galileo directed them toward the starry skies. He used telescopes to study and observe the boundless beauty of the universe. Remembered as a heroic figure who dared to challenge the established worldview of the medieval era, Galileo's work has had long-lasting consequences for humanity's fundamental understanding of the universe. To this day, the story of Galileo is truly an important example of how simultaneous developments in scientific thinking, technological advancement, and a network of combined knowledge unfolded. More than half a century after Galileo's time, Isaac Newton also began turning his gaze towards the sky. Newton's significant contributions to the development of telescopes had crucial implications for traditional refracting devices. Instead of using lenses, Newtonian telescopes utilized mirrors. While Newton was certainly not the first to consider reflecting telescopes, his version had some key advantages. It was cheaper, didn't produce chromatic aberration, and was easier to assemble and transport. However, Newton's view that reflecting telescopes were the only solution to the problem of chromatic aberration was soon proven wrong by Chester Moore Hall in 1729. Hall developed a modified lens, consisting of two types of glass closely cemented together, overcoming some issues and demonstrating that refracting telescopes could still be viable. It's unfortunate that nowadays, most telescopes used in observatories or on space stations rely on mirrors rather than lenses, and the race to build the largest devices has come to an end. However, significant advances in optics and accompanying lens manufacturing methods developed and refined over centuries have laid the foundation for our current efforts in exploring the universe and successfully crafting the most powerful observational instruments of the present moment, the James Webb Space Telescope. Few may know that the journey of this special telescope began a long, long time ago, nearly 40 years in the past. The first steps of Hubble's successor, Webb's story, begins on a morning in 1987 when astrophysicist Riccardo Gianni, then the director of the Space Telescope Science Institute, and with the Hubble yet to be launched, asked Deputy Director G. Illingworth to start thinking about Hubble's successor. My immediate reaction is, Ark, we haven't even got Hubble launched yet, and we've got a million things to do on there. It has major problems, so how can we do this as well? Illingworth recalled recently. He said, trust me, you've got to start early, because I know it takes ages to do this. Hubble had been under development since around 1970, spearheaded in its early years by the NASA astronomer Nancy Roman. Following decades of campaigning by Princeton's Lyman Spitzer, they are known as the mother and father of Hubble. Illingworth, hailing from Australia, along with his STSCI colleagues Pierre B. of France and Peter Stockman of the United States, began discussing the next-generation space telescope. Essentially, they had nothing to build upon. We started thinking about what would be better than Hubble and complement anything it does, as well as open up new areas of discovery, Illingworth stated. In the challenging budget context of 1996, a committee of leading astronomers studying the concept of an infrared telescope proposed a 4-meter mirror foldable to fit into a rocket fairing, significantly reducing costs and complexity. Illingworth thought it was crazy, it won't be as good as Hubble. NASA's leadership at the time, Dan Goldin, evidently felt similarly. At a meeting of the American Astronomical Society that year, Goldin remarked in a speech, "Why are you asking for something so modest? Why not go after 6 or 7 meters?" As committee member Wendy Friedman recalled, basically, Goldin said, "You guys are a bunch of scaredy cats." He received enthusiastic applause. Illingworth said, "In my mind, he saved the telescope. It'll be bigger in the end." The James Webb was also designed to fold. After heated discussions around an 8-meter diameter, in 2001, NASA finally decided that the segmented mirror's diameter would be 6.5 meters, providing the next-generation telescope with over 6 times the light-collecting area of Hubble. The question arose, how do you fit a 6.5-meter wide mirror into a rocket fairing that's only 5.4 meters wide? A crucial part of the design is how they fold it. External contractors developed competing mirror designs. Lockheed Martin's mirror folds like 6 petals, while Ball Aerospace's resembles the top of a falling leaf. After considering the proposals for a year, Mather and his team cherry-picked elements from each proposal. The mirrors would be made of beryllium, a lightweight, sturdy, and non-toxic material. When in powder form, beryllium gives you a stiff neck, but it's the only thing that works, according to Mather. B. Beryllium powder is pressed into blocks in Ohio and then cut into shape in Alabama. Afterward, the 18 mirror segments were coated with a layer of gold that reflects infrared light exceptionally well and polished at a facility in California built specifically for this purpose. Sarah Kendrew, a Belgian-born British astronomer working on MIRI, one of Webb's instruments, noted, "Shaping and polishing the telescope mirrors is a dark art that's been around for hundreds of years." For the sun shield, a delicate material determined the fate of the infrared telescope. The research team quickly settled on Captain, a smooth, silvery plastic that looks like the inside of a French fry bag but is as thin as a human hair. Because it can tear, the sun shield would need multiple layers for redundancy. The team decided on 5 layers, and the layers would need to be spread out, separated, and kept taut by a system of booms, cables, and strings. The propulsion system and solar panels would face the sun, while the optical system and instruments, which must operate at temperatures below 223 degrees Celsius, would be on the dark side. James Webb has many firsts, many significant firsts, and that sun shield is one of them. In 2002, the main telescope officially got its name. NASA Administrator Sean O'Keefe broke tradition by naming the telescope after an administrator rather than a scientist. For example, the Hubble Space Telescope is named after American astronomer Edwin Hubble. This choice was not immediately well received by astronomers. Last year, 11,200 astronomers signed a petition to rename the telescope, citing claims that Webb either supported or ignored the firing of gay government employees during the Lavender Scare. After an investigation, NASA announced in October that historians found no evidence warranting a name change. Now, the new chapters of humanity's history about the galaxy's past begin to be written. Despite some last-minute controversies, James Webb ultimately launched humanity's gaze into the universe. When Hubble operated, humanity immersed itself in the universe's vision like children with newfound clarity after putting on glasses for the first time. Now, we can eagerly anticipate the new discoveries Webb will bring. Humanity embarks on an adventurous journey to seek answers to questions that puzzled scientists of the last century. Where do galaxies come from? The beginning of galaxies. Many scientists, astronomers, astrophysicists, and space enthusiasts have various reasons for wanting to observe the first stars and galaxies. Some believe that Webb will see what's called population 3 stars, primitive stars, believed to be around 10,000 times heavier than our Sun. Such stars could help solve another significant mystery about galaxy formation. How do the centers of galaxies form supermassive black holes? Tiny but extremely powerful gravitational sinks that can weigh billions of times the mass of our Sun. No one knows how these supermassive black holes become so heavy, when, or why their properties correlate with those of their host galaxies. Theoretical physicists have attempted to simulate multiple times how structures could emerge in the young universe. Therefore, Webb is not the only curious explorer sent beyond the skies to verify these hypotheses. Earlier in 2009, the European Space Agency sent Planck into space to map the entire sky, hoping to observe the universe's panorama from its early days. Among all satellites sent into space to study cosmic microwave background radiation, Planck is known as the coldest object. During its 3 years of operation, the lens's signal-receiving devices were cooled down to 0.1 Kelvin to minimize the noise from the receivers and swiftly capture all anomalies in the universe's heat. The results obtained revealed that the cosmic microwave background radiation is not entirely uniform. The amplitude of the temperature fluctuations across the sky is extremely small, but it reflects a universe teeming with matter. The cosmic microwave background can be seen as an ID card containing information about the early universe. Data collected by previous space telescopes and the more recent Planck telescope have been processed using statistical techniques, utilizing the distribution and amplitude of temperature fluctuations corresponding to clusters of matter. Astronomers then used cosmological models to calculate the energy and matter components in the universe. However, they couldn't simply start with the background radiation and develop that image on a computer to see what happened. There are still too many indeterminable factors. Peter Beruzzi, a theoretical colleague of ours at Arizona who models the formation of stars and galaxies, notes, many initial conditions are not well understood, things like magnetic fields and the level of turbulence in the gas. There's still a lot to do to go from a large, slightly dense point in the background radiation of the universe to a small gas cloud that will collapse due to gravity and form a star. The time period represented by the distance between sporadic waves representing the early universe and the observable galaxies today is very distant. But it still holds immense significance. It is the ultimate answer to the question, where do galaxies come from? To trace the footsteps of the first galaxies, we will collectively rewind time to when the universe was very hot and young, the moment it was born and boiling like a bomb about to explode. In the time span from about 10 to the power of 36 seconds after the explosion, scientists have described the dramatic changes in the universe. Although the lambda-CDM model does not specify the exact cause of the explosion, during that period, an enormous surge of energy appeared and rapidly flattened spacetime. Inflation, for British astrophysicist Fred Hoyle and those who believed in the later steady-state theory, the persuasive logic is simplicity. Says Jay Gallagher, an astronomer and professor emeritus at the University of Wisconsin-Madison, that at some point, something changed, and the universe created matter. Why should it be like that? Hoyle, a proponent of the steady-state theory, believed that the opponent's belief in the Big Bang, as he named it, was influenced by the Book of Genesis. The discovery of the cosmic microwave background, as it is called, did not immediately end the debate. Those in a steady state, like Hoyle, did not believe in its explanation and clung to their theory for decades to come. But for others, those who recognized the glow of the Big Bang when they saw it, it composed a puzzle. The nearly perfect uniformity of the waves from all over the sky indicates that the early universe was incredibly smooth, a remarkably pure substance. Faber, a graduate student researching galaxies in the late 60s, says, "The paradox is that today we see a very messy universe." So the first challenge in understanding galaxies is figuring out how the universe transitioned from a smooth form to a clumpy one. Astrophysicists understand that atoms gradually come together due to gravity, eventually bursting into structures like stars and galaxies. The uniformity of radiation indicates that matter was distributed very evenly at that time, because there were no large luminous objects to stir the primordial soup. It remained smooth and uniform for millions of years as the universe expanded, and the cosmic microwave background radiation shifted towards longer wavelengths. The universe became colder and darker. Astronomers had no observations in the Dark Ages, but on paper, the development of structures seems extremely slow. We know that the primitive universe is a micro-world where physical phenomena must adhere to the laws of quantum physics. In the primitive universe, particles of matter appear and disappear instantly due to quantum fluctuations. This phenomenon, called quantum fluctuations, makes the newborn universe not entirely smooth and uniform. These quantum fluctuations initially exist at the micro level and spread across the entire infant universe after the inflationary phenomenon occurs, becoming the seeds of matter clusters scattered throughout the universe. Let's rewind time a bit more to understand this better. After erupting violently like a colossal atomic bomb and releasing matter into the vacuum, the universe began to cool down, making way for an extended dark age of over 100 million years. It started to become quiet but not peaceful. In the silence that enveloped all matter, gravity silently tightened its grip and began gathering streams of dispersed matter back together. They flowed along the waves from less dense areas to slightly denser ones. But what exactly is that flowing stuff hidden within the subatomic soup of hydrogen and helium nuclei, electrons, photons, and neutrinos? Much more was created by the Big Bang alongside atoms. The universe was filled with a vast quantity of other matter that still dominates the cosmos today. The dark matter began to flow in the darkness, dominating the gravitational pull of the universe. In the early universe, the gravitational pull of dark matter was irresistible, causing it to pool into overdense regions, drawing in other particles like nuclei, electrons, photons, and neutrinos. This process caused dense regions to grow, leading to the formation of the first whispers of galaxies. However, matter followed a different path than dark matter, as gas is extremely complicated, unlike the elementary physics of dark matter. The primordial universe was mainly filled with hydrogen, helium, and dark matter, with some regions denser than others. Gas could collide and shock, heating up and, crucially, cooling down. So when the universe was about 100 million years old, the gas was dense enough and cool enough to fragment. Finally, these fragments collapsed under the continuous force of gravity. As they collapsed, the density of the fragments increased, and they became more spherical. The core temperature of these fragments skyrocketed, and nuclear reactions exploded. Eventually, the first stars in the universe were born, and light finally began to return to the cosmos. However, these first stars were quite different from modern-day stars. They were entirely composed of hydrogen and helium and were massive, more than 100 times the mass of our Sun. They would shine for a few million years, before dying in a supernova. Despite their short lifespan, their intense light, primarily in ultraviolet and X-rays, reshaped the universe once again. This radiation sprayed into space, illuminating the sky. However, the high-energy photons also struck the massive hydrogen clouds around them, ripping off their electrons and ionizing the gas. More and more matter transformed back into plasma, a state that persists to this day. 99.9% of all the atomic matter in our universe exists in an excessively hot ionized plasma state. When these first-generation stars burned out and met their demise through their deaths, they pounded the universe. The first galaxies emerged. As the first stars began to shine, ionized gas bubbles formed around them, gradually expanding. When more and more stars formed over hundreds of millions of years, the ionized gas bubbles merged with each other, and eventually, the intergalactic gas was completely ionized. Because the first stars were extremely massive and had very short lifetimes, only a few million years, they became gigantic nuclear reaction furnaces in the universe. Some stars, after their death, will explode in supernova events, releasing the metals they produce. Stars with masses between 100 and 250 times that of the Sun are predicted to be completely destroyed in extremely powerful explosions, and most of the first stars are estimated to fall within this mass range. Because metals are more effective than hydrogen in cooling star-forming clouds and allowing them to collapse into stars, even a small amount of metal production and release can contribute significantly to star formation. At this point, the reionization role of star systems came to an end. The chemical enrichment process of the universe has begun and continues, while gravity remains steadfast in its unchanging nature. Like an invisible thread, gravity continues to pull matter and tighten it together, leading to the development of inhomogeneities. Eventually, stellar groups merge, forming larger star clusters, marking the birth of the first galaxies. The exact moment a galaxy is born cannot be precisely determined due to the significant density fluctuations caused by quantum fluctuations. While the first stars emerge, the galaxy's developmental process persists. Galaxies gradually evolve through the accumulation and collision of substantial matter blocks known as bright knots. These bright knots consist of dark matter, gas, and stars bound together by mutual gravitational forces. As time progresses, larger and more massive bright knots gain dominance, becoming the future growth sites for galaxies. As their gravitational influence increases, their dominance rises, attracting more matter into their control and providing raw materials for future generations of stars. The early stages of galaxy development are uneven, with most small galaxies remaining small and evolving slowly. Larger and more intense galaxy development is much rarer. Indeed, the vast and varied mass of galaxies still leaves its mark on the universe today. For the smallest galaxies, these early stages of life are quite perilous. They might host a giant star burning brightly for a few million years, only to turn into a supernova, with the powerful aftermath of their death driving away all other gases in the galaxy. The weak gravitational force of a small galaxy disperses this gas into the universe. The star-forming life of these young galaxies ends before it truly begins. Many of these extinguished small galaxies likely lived in the early universe halos of dark matter, devoid of all atoms and all stars. These dead, elusive ghost galaxies were doomed to remain dark and unseen, and they should still fill our universe today. But more massive galaxies were different. In a larger galaxy, gravity could draw the gas back in, being recycled into the next generations of stars. So, while many galaxies were snuffed out in the early cosmos, others continued to grow, fat on the stars and gas they consumed in their deep gravitational wells. New stars were born, lived, and died, but these were different from the first generation of stars. Through each generation of stars, heavier elements are expelled and contribute to polluting the universe. While these elements still make up a negligible amount compared to hydrogen and helium, their presence strongly influences the life cycle of their host stars. Heavier elements mix into the layers of stars, altering their opacity, a measure of how easily the nuclear energy at the star's core can escape. In the process of trapping radiation, stars like our Sun begin to be born with longer lifespans and fewer explosions. Billions of years after their formation, some galaxies become more peaceful, but violence still exists in the universe. This violence dates back to the beginning of time and led to the creation of some of the most extreme environments in the cosmos. To understand how the first galaxies evolved into the galactic zoo we see today, we need to go back to the mid-20th century when astronomers faced a cosmic-scale mystery. Modern galaxy in 1932. During the early days of transatlantic radio communication, a man named Carl Jansky was puzzled by a persistent background hiss present in transmissions. Although he wasn't surprised by the existence of this background static, what befuddled him was its regular and precise timing. Jansky noticed that the static varied with the time of day, differing in intensity on a regular schedule. He was amazed at how his electronic equipment was able to determine the time of day when he was taking his measurements. As his observations continued over weeks and months, he observed that the static was not quite aligned with the 24 hours of the solar day but was slowly and steadily drifting across the sky. This led him to realize that the source of the radio noise was beyond the Earth and the Sun and resided deep in the heavens. During that time, many astronomers were observing the skies using their telescopes, focusing on the optical light that was known to come from stars and galaxies. However, Jansky had a realization that another form of electromagnetic radiation was coming from the universe. This led to the birth of radio astronomy. Unfortunately, Jansky wasn't able to further contribute to laying the groundwork because his employer Bell Labs assigned him other tasks. Nevertheless, his name is still remembered and used as a unit of measurement for the intensity of radio waves from space. After the discovery of radio waves from outer space, the scientific community became interested in studying them further. Researchers in the United Kingdom and the United States detected radio waves from the Sun, while Grote Reber built the first functional radio telescope and became the first radio astronomer. In a decade, Reber's work revealed that the Milky Way emits radio waves. Subsequently, astronomers discovered many more sources of radio emissions throughout the sky. These sources were powerful and came from small points scattered all over the sky. They were identified as quasi-stellar radio sources, or quasars, and were found to be spread throughout the universe. Today, astronomers know of more than 1 million quasars. They are powered by supermassive black holes, each with masses that are more than 1 billion times that of our Sun. These black holes are so powerful that they can be seen from vast distances away, taking us back in time more than 10 billion years to the earliest epochs of the universe. It is believed that these supermassive black holes formed from the deaths of supermassive first stars and, after feeding voraciously and merging, became the central gravitational point of many larger galaxies. For the first few billion years of the universe, it was a hub of activity. The first stars, galaxies, and quasars shone brightly. However, after this initial period, the universe began to calm down. The pace of star formation has been decreasing continuously over the last 10 billion years, but galaxies have continued to evolve and change thanks to gravity's infinite pull. Some galaxies have been shaped by their spin. Cooling galactic-scale gas has collapsed into a flattened pancake that fragmented into stars. This immense disk of stars has become the defining feature of these galaxies, the beautiful spirals we see through our telescopes today. On the other hand, for some galaxies, the journey to spiral beauty was cut short. Collisions between more massive galaxies have violently torn them apart and robbed them of their spine. These galaxies transformed into more formless objects, elliptical galaxies, the other major galaxy type observed in the heavens. Elliptical galaxies and spiral galaxies are not the only designs of galaxies that astronomers can see. There are also irregular galaxies, which appear to be misshapen and are believed to be a result of recent galaxy interactions. These galaxies are in a state of transformation and have yet to settle into a defined shape. They provide a glimpse into the potential fate of our own galaxy. Astronomers have estimated that there might be as many as 1 trillion galaxies present in the observable universe, varying in size from small to immense. Most galaxies are relatively small, containing only a few billion stars, while the largest is over 200 times more massive than our own Milky Way. The discovery of galaxies was quite surprising, but even more so was the realization that they are not randomly scattered throughout the cosmos. Quantum seeds imprinted at inflation through the action of gravity are formed into a complex network of mass known as the cosmic web. Volumes of underdensity are emptied out, with matter drawn towards more massive regions, while some galaxies and dark matter remain. These sparse regions can extend for millions of light years. The outflowing matter gathers into immense sheets and filaments and continues to be drawn toward the most massive objects in the cosmos. Have you ever wondered where all the galaxies are headed as they journey through the vast voids, sheets, and filaments of the universe? In this complex network, dark matter is distributed like a sponge, creating superdense regions that serve as the ultimate gravitational destination of all matter. But these regions are known as galaxy clusters, which are incredibly fascinating places that are home to thousands of galaxies. These galaxies orbit around dense halos of dark matter that greatly outweigh all the stars, making them the most concentrated mass in the entire universe. Deep within the heart of galaxy clusters sit truly immense monsters, the most massive galaxies in the entire cosmos, known as CD galaxies. They are true giants of the universe, built from hundreds of trillions of stars and shrouded by a massive amount of dark matter. These cosmic behemoths sit deep within the well of gravity and are surrounded by thousands of other galaxies. Astronomers have observed that clusters themselves cluster together, forming even more immense structures called superclusters. In our patch of the universe, we are embedded in the Laniakea supercluster that contains many millions of galaxies. However, it is still up for debate whether they are bound together by gravity. Just like galaxies, clusters of galaxies come in a vast range of sizes. For every monstrously large galaxy cluster in the universe, there are many smaller clusters. And for each of these smaller clusters, there are countless galaxy structures known as groups. Most galaxies in the universe exist in groups. These groups typically consist of one, two, or a few larger galaxies that are similar in size to our own Milky Way. Alongside these larger galaxies are numerous smaller galaxies, possibly hundreds of dwarfs, all held together by the mutual gravity of each other and the dark matter that surrounds them. Our Milky Way galaxy is a part of a group of galaxies, which we share with the Andromeda Galaxy. This group is called the Local Group, and it is home to many other galaxies. Some of these galaxies, such as the Magellanic Clouds, are visible to the naked eye, especially in the southern hemisphere. However, more than 100 other galaxies are held together by the gravitational force of the Local Group. Most of these smaller galaxies have been discovered only in the last few decades, thanks to the new telescopes that can peer deeper into space. The presence of all these smaller galaxies orbiting the larger ones has revealed something important to astronomers. The epic of galaxy evolution is far from over. When giants eat their own kind, we often talk about tides in the context of the moon pulling on Earth's oceans and creating tidal phenomena, and this is partly true. But from a galactic perspective, tides are a less highlighted process. The smaller galaxies near larger ones will experience stronger gravitational forces, while those farther away will experience weaker forces. As a result, the smaller galaxies will stretch and eventually break apart under the gravitational